All right, today we're going to take a look at chapter 8 in your textbook. There are 2 chapters on chemical bonding, and that's not by accident. There's a lot of material that goes into understanding the chemical bonds. At this point in the course, we've sort of got a practical knowledge of bonding based on the types of reactions we've studied and how they generate heat or they absorb heat. But in order to be able to make predictions about how things react and whether they're exothermic or endothermic or whether they're just virtually forbidden to happen, we need to gain an understanding of the bond itself, the chemical bond. So that's going to be the purpose for these last 2 chapters in the semester. And I've got the usual set of documents, the PowerPoints for chapter 8, the review document. There have been a couple of different versions. This is version 1. And so when you look for the worked problems in Brightspace, be sure you're getting the worked problems version 1. It'll go with the review document version 1. All right. So I didn't ask my usual questions. Any problems we need to deal with before I start expounding? Okay, I'll take that as a no. All right. So we're going to start off with bonding and general concepts. And in fact, general concepts are going to be in terms of, in the beginning, predominantly ionic type bonding. And in chapter 9, we get into more depth. Now, we're going to get some covalent bonding toward the end of this chapter. But we really develop the ideas of covalent bonding in chapter 9. So we bat these words around, chemical bond, as if we know what we're talking about. But what is a chemical bond? You can make it really, really simple, or you can complicate it. And we're going to start off simple, of course, and then try to gain some more knowledge about the bond. All right. Okay. So with simple bond is just a bond is our way of expressing the forces that hold atoms together in a molecule or in an ionic arrangement, crystal. Why do atoms bond to each other to form compounds? Why don't they just stay individual atoms? Wouldn't they be happier? Right? They'd have all their own electrons and they wouldn't have to give any away. It's chemical bonds form because it's mutually beneficial to the atoms. We've talked about it a little bit as we go along, atoms trying to acquire an octet in their valence shells is one way of expressing it. So if the atom, and the other way, which is kind of a corollary to the octet, is the atoms are trying to look like noble gases. Noble gases are very stable. They have an electronic configuration that is complete. It doesn't need to give up any electrons, doesn't need to accept any electrons. And in a manner of speaking, that's where elements are heading when they form bonds with each other. All right, we've flogged this horse several times in the past. How do atoms bond with each other? We've described them as either ionic bonding or covalent bonding. In other words, there's a complete transfer of electrons, or there is a sharing of electrons. we got our first big theoretical kick to understanding bonding with Dalton's atomic theory. With Dalton's atomic theory, it really just laid the foundations for understanding why chemicals react with one another. But it didn't explain actually the true driving force for why atoms associate with one another and rearrange it. It didn't address the problem of chemical bonding. Okay, I mentioned earlier, chemical bond can be thought of as a force, right? If there's more force holding atoms together than there are forces pulling them apart, then you'll have a bond. So we talked about forces that hold atoms together, but what kind of forces can pull them apart? Well, if they interact with other molecules or other atoms, then there's a force pulling on the atoms in that molecule. So if the force that's pulling them apart is greater than that holding them together, then they won't survive as a molecule. So it's always a balancing act. One thing we do know is that if we budget or follow the amounts of energy that are available before a reaction, and then we assess the energy levels after the reaction, we find that molecules form or bonds are formed when the energy of the aggregate is lower than the energy of the individual atoms. Or if we've got molecules coming together for a reaction and the atoms are going to rearrange, they don't rearrange typically unless there's an energy advantage to it. In other words, we're talking about stability, energy stability. If there's stability to be gained by lowering the overall energy of the products versus the reactants, then you get a reaction. And the bonds that form are more stable, typically, than the bonds that you had before, if there were any. Now, there's some the natural inclination for someone who's really curious is to say, well, then why do we even form explosives? Right? How can you store energy in an explosive if it's supposed to be more stable than the products? Okay, I hope I'll address that eventually. It's a localized minimum, let's put it that way. A localized minimum for the explosive is lower than the products of an explosion or the products of the reactants that go in to make it. So the system is trying to establish the lowest possible energy it can obtain under the circumstances. All right, so here we have our example for an ionic bond. Sodium ion and chloride ion are close enough to each other that they have reached a minimum energy level. If we try to push them any closer, then the nuclei start interacting, and the nuclei are always positive. So you get that repulsion. So they can only get so close before you lose your advantage. The energy advantage is lost if you push them too close. But if you pull them farther apart, then they don't feel their electrostatic attraction anymore. It's not strong enough to hold them together. So there's an ideal minimum distance between the two that establishes this ionic bond. And it's been determined to be 0.276 nanometers. So they're really close. And we can calculate For ionic bonds, we can calculate this interaction using Coulomb's law. And if you've had a physical science course or if you've had physics, then you'll make the connection to Coulomb's law. Coulomb's law simply states that the energy of attraction between the two charges is proportional to the magnitude of their charges. Right? And if they're equal, if they're both positive, then you get a repulsive force, and if they're positive negative, you get an attractive force. But it's still a measurement of force. This is well, actually, it's energy, not force. Energy. So it's proportional to the magnitude of the charge on either party, and inversely proportional to the distance between them. So as the distance gets greater, the energy goes down. And that works from the minimum distance of bonding out. Like I said, if you get them too close, then you start interacting with the nuclei. So this Coulomb's law only works. That should be a dot. Joule nanometer is this is a constant. This is Coulomb's constant, right? You don't have to worry about that if you needed it to be in the useful information, I think. Let me just be sure. Okay. What was it? 2.31. So constants. Okay. So you must not need it for illustrative purposes. Okay. Okay, so for these two charged particles, the amount of energy that is, if it's negative, remember, relative to the system, if it's negative, then the energy is lost to the system. And the larger the negative, the stronger the bond. Stronger the attractive forces. Okay. So what happens, let's look at hydrogen. Hydrogen is dihydrogen. The way hydrogen exists at 1 atmospheric pressure and room temperature is like the other diatomics. Since they're two of the same atoms with the same element, then you're not going to get an electrostatic attraction. This has to be covalent. So we can't use electrostatics to explain the bond between two hydrogen atoms. What you get is a sharing, or in terms of what we've learned so far about orbitals, is you get an overlap. Right? So here are the free atoms, and they come closer and closer, and you start to get an overlap of the orbitals. So you have a larger space, a larger probability that's available for the electrons that are shared. In this case, only one electron from each. The electrons that are shared now have a greater space to exist in their probable forms. Right? Remember, when we talk about where electrons are, we've opted, by way of the Heisenberg uncertainty principle, to go with probabilities for locations so that we can actually calculate energies. So once they get to a certain distance, you get an ideal overlap. And one thing that is consistent between the two, the ionic and the covalent, is that this is a minimum energy state. These two atoms are at the perfect distance to minimize the energy. In other words, they had energy here, and the energy of combined energy went down to a minimum, and that's where they bond. we're looking at a balancing act. Right? We've got one proton each and two electrons, and you have repulsive forces between the protons and the electrons. But you have also attractive forces. Now we're looking at it in terms of electrostatics. Attractive forces between the proton of one atom with the electrons of the other atom. And that also comes into play. This is an illustration. The best way to look at this graph is not to go from left to right, but to go from right to left. So these are the separate atoms, and they're getting closer and closer and closer. This is the internuclear distance. Closer together, and the energy starts to drop as they get close. And at a certain point, this distance, 0.074 nanometers, they form an ideal situation, a bond. And if you try to push them together closer, then the amount of energy required goes way up. That's why the nuclear reactions that occur between hydrogen atoms in stars only occurs deep in the star under extreme pressure and temperature, because they have to overcome these repulsive forces in order to get those nuclei to fuse. Okay, so then we're not talking about chemistry anymore. We're talking about nuclear physics. So once you get past here, we don't have to worry about it. All right. Come on, everybody. Okay, just to review, the key ideas for ionic bonding is you have opposite charges attracting one another. Electrons have to be transferred in the process in order to make the oppositely charged ions that then attract. Covalent bonding is just electrons are shared. There are intermediate cases, of course, and no bond is, I mean, even the ones that we consider virtually pure ionic bond, they still have some covalent character to them. And vice versa, covalent bonds will have a certain amount of ionic character to them. And that leads us to the concept of polarity. When a bond is formed, unless the bond is formed between two identical atoms, there will be a certain amount of polarity to the bond. And what do I mean by that? Well, if we have our two hydrogen atoms bonded together, then we have equal attraction of electrons, both for either one. But if we have, say, hydrogen combined with fluorine, we're gonna put numbers to this in a few minutes. But the fluorine has a stronger attraction for electrons. Now, it's not strong enough to make ions, but it is very, very strong. And it tends to pull the probability cloud, so to speak, of electron density toward the fluorine more than the hydrogen. So the hydrogen becomes deficient in electron density, and fluorine becomes excess in electron density, which means that this one is slightly negative and this side is slightly positive. And that means the bond has to be polar. It's kind of like right, bar magnet, South Pole, North Pole. Well, in this case, this is going to be slightly negative. We use a small delta for a Greek letter to designate either positive or negative. And sometimes we say the bond is polar. This way, that plus is on the side of the positive, and the arrow points toward electron density. And there are gradations of polarity of all bonds. And we're gonna cover how to determine. We haven't done that yet, have we? I don't think so. Okay. So if there is equal sharing of electrons, we say that the bond is nonpolar, but it's covalent. Obviously, it's covalent because neither atom can win and remove electrons from the other one. So it has to be covalent. And it's also non-polar. Okay. Polar covalent bonds, on the other hand, are like this one. We have an unequal sharing of electrons. It's not so much that you break the covalent character of the bond and form an ionic bond, but it is enough that you shift the density toward one atom or the other. And this charge separation gives you a slightly positive or negative charge. So what are the implications of that polarity? Well, you can see it in things like melting point or boiling point. For nonpolar molecules, the boiling point is very low, right? Since you don't have a separation of charges, you don't have any electrostatics to deal with in a significant amount. So these hydrogen molecules in pure hydrogen don't attract one another very strongly. That means that just a little bit of energy and they're gases. Or you take away a lot of energy, cool them down, and they'll turn liquid. But they have to be very, very cold. In fact, liquid hydrogen is, it is the coldest substance that we can produce industrially speaking. But something like hydrogen fluoride, while it's a gas at room temperature, we can turn it into a liquid much easier than you can hydrogen. Just cool it down a little bit and it'll turn liquid, because there are interactions between these negatives and positives on neighboring molecules that hold it together. So that's part of the evidence for polarity. We know polarity exists because that's the only reasonable explanation for these differences in boiling points and freezing points. You can actually measure the polarity. So we have this HF molecule, and it's between two plates, right? And we have sensitive instruments that can judge the charge between the plates. And if you vary the charge on the plates and measure the induced charge between the plates, then you can tell exactly when these molecules line up with the negatives toward the positive plate and the positives toward the negative plate. But you can do a scan of charge over time, and you can actually see when it happens. And that tells you what the charge is, and you can relate that to the actual polar charge of each of the molecules. Okay. So there's our definition for a chemical bond so far. Force that holds groups of atoms together, makes them function as a unit. Okay, I'll go with that for now. Why do they bond with each other? The best explanation is to watch the energy. Is the energy after the bond lower than before the bond? Well, it should be. If our definition is correct, then that's the impetus for forming the bond, is the after part is more stable than the before part. And atoms bond with each other either by sharing electrons or transferring electrons from one to the other, and then you get electrostatic attraction. Okay. So here's the term electronegativity. I mentioned the strength of attraction of fluorine is greater than hydrogen. Well, every atom in the periodic table has a characteristic electronegativity. It has a strength of attraction for electrons. And if you compare those values that have been assigned for each atom, say you have this atom of a different element, and you say, all right, what's the attraction? Right? Is it going to make it an ionic bond, a polar covalent bond, or a purely non-polar covalent bond. And you can compare the numbers that are associated with them and determine roughly what's the character of the bond. This electronegativity was first proposed by Berzelius in 1811. Berzelius was a, I guess since he's famous, he had to be brilliant, Swedish chemist. And he wasn't the only one studying it. Oops, wrong button. This is an attempt at a quantitative description of atoms and the character of the bonds that form between them, trying to get a handle on the nature of the bond if we know something about the atoms before the bond forms. And it's a measure of this attractive force of the atom for electrons. We've sort of been introduced to that at this point. Up to this point, remember electron affinity? Electron affinity is an actual measure of how attractive an atom is for an electron. But that atom stands alone, and it's attracting an electron as if it were in its own little universe. There's a slight shift in understanding when we go from electron affinity to electronegativity. Electronegativity assumes that one atom is in the vicinity of another atom. And in fact, that's how it is measured and calculated, based upon its formation of a bond. And one of the first quantitative scales that was used was developed by Linus Pauling in 1932. It's not the only scale, but it seems to be the most popular one. And there's a formula that goes with it, and it's based upon bonding atoms with other atoms, and it's beyond me. Incidentally, Linus Pauling was one of those scientists who comes along every now and then. Most scientists are analysts, and I mean that in the definitional sense of the word. Analysts tear things apart and see what they're made of. That's most scientists do that. Every now and then, you get one who comes along who's a synthesizer. They take all this research results, disparate information, and pull it together into a coherent story. And that's what Linus Pauling did. He actually wrote a book called The Nature of the Chemical Bond. And it was significant enough in the scientific community to get him a Nobel Prize in 1954. He was one of the few persons to also get a Nobel Prize in a separate arena. And he got a Nobel Prize, a Peace Prize in 1962. He actually did something during that, not like Barack Obama. All he did was get elected president and they gave him a prize. That shows you how the Nobel committees have degraded themselves over the years. Anyway, so Pauling's method for determining electronegativity would take, for example, would take an atom of some element bonded with hydrogen, and then it would also, you can calculate the bond energies fairly easily for different molecules, and you try to keep them simple, right? So there are fewer complications. And then you take the bond energy between the two hydrogens and the bond energy between the two atoms you're investigating, and you add them together and divide them by 2, and you compare them to And that, in fact, is the expected bond energy of the hydrogen with our mystery element. Well, when you measure the bond energy, the actual bond energy of this, it won't be the same. And that difference is attributed to a difference in electronegativity between this one in that form, as in the true form, the molecular form, and the calculated version. And that becomes the electronegativity value. So, since we're talking about forming bonds with other atoms and we're using hydrogen as our reference point, electronegativities are always relative calculations. There's no way to determine them in an absolute sense. Oops. Okay, so this difference here is an indicator of the bond polarity. That calculation that I was trying to explain in words, there it is in print. Actual minus the expected. If this change, this delta is 0, then we say that the bond is nonpolar. And the only way you can guarantee that is if both atoms are the same. Right? If both of these are hydrogens, then we would expect this one to be the same as that one. All right. Pauling took the periodic table and he did these calculations on all the elements that he had information for and put those numbers in a periodic table, and we see a trend developing. We see that the electronegativity of these elements increases from lower left to upper right. Right? And that is consistent with our investigation in the last chapter of electron affinity. Right? A stronger attraction for electrons means a more negative value for electron affinity. And the most negative value is in the upper right-hand corner, fluorine. So lower left to upper right, we have a stronger electron affinity, a more negative value. And in Linus-Pauling's system, the highest electronegativity is an expression of strength of attraction for electrons by fluorine, and that's given the number, based on that calculation, that number is 4.0. And in the lower left-hand corner, down around cesium or francium, they have equal numbers, is 0.7. So the metals tend to have a very low electronegativity, and the non-metals have a higher electronegativity. That's why early on in this course, we said ionic bonds generally form between metals and non-metals, because the difference in their electronegativities are far enough apart that the non-metals are going to take electrons from the metal, make it a cation. Now, the non-metal becomes an anion. That's the reason. Well, that's the quantitative reason. So here's a representation. Notice that it kind of, if you stay in the representative elements here and here, the trend is fairly consistent from here on up there. Once you get into the transition metals, it kind of roller coasters. And they're all fairly similar. 1.3, 1.2 up to 2.2, 2.4. And you get this dip in the middle. 1, 2, 3, 4, 5 dip. Remember the d orbitals? 10 electrons, 5 electrons in the d orbitals is half filled. There's an electron in every sublevel. So that tends to stabilize it. And then when you get this an extra electron, now it's paired up with another electron. And plus it has an extra proton. for attracting electrons. All right. So let's see if that trend, if we can use that trend to answer these questions. If lithium and fluorine react, which has more attraction for an electron and why? Well, look where they are on the periodic table. Lithium's way over there on the left, fluorine's way over here on the right. So lithium should be the lower electronegativity, fluorine should be the higher. So the higher attraction, of course, is going to be fluorine because its electronegativity is higher. And in a bond between fluorine and iodine, which has more attraction? Well, fluorine is at the top of the halogens, ions toward the bottom. So the trend says lower left, upper right, which means you go up, you have more attraction. So fluorine is going to have more attraction for electrons than iodine. Here's the explanation, and it's similar to the explanations that we had for the other trends in the last chapter. Across a period, the number of protons are increasing, and that means the effective nuclear charge is increasing, but you're not adding any energy levels of electrons to the outside. So the sum game is that the protons, the effective nuclear charge is increasing from left to right, which means it's more attractive toward electrons from the outside. How about up and down? If you go down a group, then the electronegativity is decreasing because the size of the atom increases, and there are inner electrons that you're adding as you go down, different energy levels. And they are shielding the nuclear charge from the nucleus, which makes it less attractive to external electrons. Okay, so I mentioned earlier this trend. If you can, not trend, but a calculation. If you have two atoms and you know their electronegativity numbers, and we're sticking with the Pauling scale, then you look at the difference between their numbers. You just take the big one and subtract the smaller one. And if that value is between 0 and 0.2, then you say that the bond is essentially nonpolar covalent, because they're close enough together, and nobody's really going to win in a tug of war between electron densities in a covalent bond. If the difference in values is between 0.3 and 1.4, then we can say the bond is still covalent, but is significantly polar. And of course, the bigger the number, the more polar it is. And then if it's greater than 1.5, greater than or equal to 1.5, we'll say that bond is ionic. Right? There's significant difference in electronegativities that one of those atoms is going to win and take electrons from the other one. Now there's one that I left out in here. Let's see. I think it's this middle one, where we go from 0.3 to 1.4 difference. We're saying it's polar covalent. But that is for non-metal, non-non. If, however, you get a non-metal and a metal bonding, then there's a division in here, and I think it's in the neighborhood of 1.2. If it's a non-metal metal, then and the difference is between 1.2 and 1.4, we also say that is ionic. Whereas if it were non-metal, and the difference is that it's polar covalent all the way across. I'm not sure if I have another slide on that or not. All right, which one of these are most to least polar? All right, we're not given any numbers here. Right, so we have to reason this one out. Most to least polar. Well, my question is, are there any metal nonmetals in here? No, I think they're all nonmetals. Yeah, okay. Why do I say that? Well, if you've got a metal and a nonmetal, then polarity of a bond is irrelevant because they're two ions. We don't call ionic bonds polar, right? Because they're separate ions. If there's a covalent bond, then we can talk about uneven distribution of electron density in the neighborhood of that bond. So since they are all nonmetals, now we can go ahead with it. So how do we tell? Well, for the first one, notice that each one of these is bonded to fluorine. So what we can do is we can say which one's closest to fluorine. That would be the least polar. So we look on our periodic table. They're all in the same period. So the one closest to fluorine is oxygen. This would be the least polar. Okay. Which would be the most polar? The one that's furthest from it, nitrogen and fluorine. And then carbon is in the middle. No, I'm sorry, carbon is furthest to the left. My mistake. Nitrogen and fluorine is in the middle. So it should be carbon, nitrogen, oxygen. There we go. So that's the first one, from most to least polar. That one was fairly easy because one of the elements was common to all three. But now we have carbon and fluorine, nitrogen and oxygen, and silicon and fluorine. So how do we deal with that one? The best way to approach this one is say, how far apart are each of those pairs on the periodic table? Like how many steps, how many elements apart are they? The closest ones together are going to be the least polar. So it's not that one. In fact, this is the most polar. Nitrogen, oxygen, right next door to each other. Silicon and fluorine. Well, actually, silicon and fluorine are further apart. So that means carbon and fluorine go in the middle. Right? So these are furthest apart, both horizontally and vertically. Then carbon and fluorine, then nitrogen and oxygen, I think. Yeah. At least I agree with the slide. And the next one. Well, the least polar, obviously, is going to be fluorine and chlorine because they're the same molecule. In fact, they're not even polar. Let's see, boron and chlorine. They're pretty far apart. Boron and chlorine. And then what's left over? Sulfur and chlorine. Yeah, they're right next door to each other. So that should be the arrangement. Let's see, who showed up? Oh, Michelle. No, Michelle's been here before. Somebody must be having connection problems. Anderson, no, I still don't see Brittany. Okay, any questions about that one? And that's if you don't have numbers. If you got numbers, it's easy. You just do the math, compare the numbers. Now here we introduce the idea of if they're going to be polar, then they can't be ionic, which would still be considered polar covalent. Well, they can't be ionic, right? So magnesium and oxygen are out. That's a metal and a non-metal. And they can't be polar if they're the same atom, the same element. So that one's out. So now we just compare this one, and this one. Least polar. Nitrogen and oxygen are right next door to each other. I would say nitrogen and oxygen would be the least polar. And you can also, since we have the table, you can compare the values. Nitrogen, oxygen, 3 to here's 0.5 difference. Silicon and oxygen would be 1.7. So that's more polar. Carbon and oxygen is 2.5, is 1. So you can do the calculations also and make the comparisons. Most polar without being considered ionic. Most polar. All right. So that's not ionic. That's ionic. This is non-polar. So we would most polar without being considered ionic. Most polar. Silicon and oxygen. Yep. Because that's 1.7 apart. Oops, carbon and oxygen. Without being considered, oh, my mistake. Notice that the difference here between silicon and oxygen is 1.7. What was our breaking line? 1.4. 1.4 to 1.5. So it's greater than 1.5, so it would be considered ionic. The problem is that these are both non-metals. So there would be some controversy. I mean, you could go to a dinner party and have a night's worth of arguments with other chemists about whether it's polar or non-polar or ionic. But for the purpose of, based upon our definition from the previous slide, carbon and oxygen would be the most polar without being ionic. And so we set up the parameters, or at least I did on the slide. So I have to live with it. So what's a dipole moment? Well, if you've had physics, you know what a moment is. It's an expression of force in one direction or the other. In a dipole, that moment, that force is due to a difference in charge. And if we have two atoms and one of them is more electronegative than the other, then it's going to be slightly negative, this is going to be slightly positive, and the bond between them, this is our expression for the dipole moment. We use that arrow with a plus on one end. Like that. Now, this is for a bond. This is an expression, this is the dipole moment of the bond. But this is also the dipole moment of the molecule if there are only two atoms present. What if you have 3, 4, 5, 6, or 100 atoms in your molecule? Can you generalize about the polarity of the entire molecule? Well, to a certain extent we can, but we need to know two things. We need to know the dipole moments of all the bonds in the molecule. Okay. which ones are polar, right? Some bonds will be nonpolar. But what are the polar bonds in the molecule? And then where do they point? This is a concept, this is actually a skill or a procedure that we use. In fact, I was first introduced to it in physics. It's called vector summation. Water molecule is a good example. Got an oxygen here, and this is the geometry of the oxygen molecule. Okay, oxygen is more polar than hydrogen. It has a higher electronegativity, so the bonds are going to be polar this way. Okay. Well, if the bonds were opposite each other like this, they would cancel each other out, and the molecule would be nonpolar. But the geometry says that they're both pointing in generally that direction. Vector summation says if we represented that polarity with a single arrow, how big would it be and what direction would it go? And it would go like this. So the whole molecule is polar toward oxygen and non-polar toward, and it's polar, negative polar toward oxygen, positive polar toward the hydrogens. And the vector summation, well, everybody knows what summation is, like 2 plus 2 is 4. At least it was when I went to school. But vector summation takes what is the component of this going in that direction, because some of it will go that way and some of it will go this way. So how much of it goes this way, then you can add them together. That's vector summation. But to sum things up, let's see, maybe it's on the slide. You need to know the individual bond polarities, and you need to know the geometry of the molecule. And we're headed that way. We're going to talk about that. Maybe not until next chapter. No, it could be this chapter. Let's see. We got to get several things under our belt first. Yeah, we do. We do talk about geometry in this chapter. So I guess I better get a move on. So I've already talked an hour. I don't even know how many slides I've covered so far. Not many. Okay, so that's a representation of the water molecule. And just what I said, the bond polarity is this way, overall polarity is that way. And this is a representation of the electron density. The more red it is, the higher the electron density. Probability of electrons in this area, the lower probability of electrons in this area. Carbon dioxide is an example of a nonpolar molecule, where the bonds are actually polar toward oxygen, right? Either direction, but they're equal and opposite, so they cancel each other out. Now, we still get this probability distribution of electrons over here and electrons over here. But for the entire molecule, they sum to zero polarity. And by the way, that should be a double bond. Okay. So if we're going to talk about molecular geometry, we need to know something about regular three-dimensional objects. Everybody had geometry? Okay, so you're familiar with regular shapes. This obviously would be linear, like carbon dioxide. This molecule, which has a central atom and 3 atoms or groups in this direction around it, their arrangement is most stable when they're the farthest apart from each other. I'll define that in more detail later. But that arrangement is it puts them on the same plane, but they're pointing to apexes of an equilateral triangle. So we call that a trigonal planar arrangement. Right, there's an example. This one has a central atom of carbon and then chlorines here, 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 and here. And notice the vectors, the arrows are here toward oxygen in these two cases and toward chlorine in these cases. Chlorine is more electronegative than carbon. So how do they arrange each other so that they're furthest apart? Well, they point to the apexes of a tetrahedron, right? A triangular based pyramid is a tetrahedron. Okay. There we go. All right, so we're going to leave that for now, the geometry, and we'll come back to it. I mentioned this earlier. Atoms that are most stable tend to have the same, they're isoelectronic with noble gases. They have this octet in their valence shell. Now that works when you have an S and a P arrangement, right? Because you can have 2 maximum here and 6 maximum there. That gives you 8, your octet. So these could be 2s, they could be 3s, 4s, whatever. And that works fairly well for the representative elements. And it's when you get into the transition elements that it kind of falls apart. But most of the interesting, well, I wouldn't say interesting, most of the well-studied reactions occur between elements that are in the second and third period, and on the first period because hydrogen's involved. So the octet rule is helpful for those types of reactions. Here we go. So these exceptions to the rules occur usually in period 4 and higher, because you're starting to get into the availability of d orbitals, and they don't behave. They're not octets, right? How many electrons can you have in a d? 10. Right? So if you've got an S and a P and a D, you're 18, not 8. Okay. Now, if we look at 10, 10 can form a 2+ ion or a 4+ ion. And I think we looked at that during our review for this last exam. Right? We had an S with 2 electrons and a P with 2 electrons. And if you lose 2 electrons from the P, which is higher energy, you get a 2+ ion. And if you lose all 4 of them, you get a 4+ ion. So that's why that explains 10's preference for 2+ and 4+ ions when it forms ionic compounds. And similarly, lead. Let's see, 10. Yeah, they're in the same group. 10 and lead are in the same group. So they have the same number of valence electrons. Bismuth is to the right of lead. So bismuth would have, let's see, 1, 2, 3, 4, 5, 6 would have a 6 S2 and a 5D10 and a 6 P3. Right? So if it loses these 3, then it makes a 3+ ion. If it loses these 3 and those 2, it makes a 5+ ion. That's good. I don't know if it's an explanation or a rationalization, but it works. Explaining how these ions form and why they form the way they do. Tellurium. Tellurium is in the boron group. Right? So it has 2 S electrons, valence electrons, and 1 P. So if it loses 1 P, it's here. If it loses all 3 of them, it's here. So when two nonmetals, those were metals, when two nonmetals combine and form a bond, they do so in such a way that they complete each other's valence shells to the noble gas configuration. But we don't add enough electrons so that each one can have the noble gas configuration. They're sharing electrons. So if oxygen is bonded to hydrogen, which is not a really good example because this is a duet, right? So it would have 1s2, and oxygen would have a 2p, would have a 2s2 and a 2p6 if they were noble gas. Right? This is like helium and this one's like neon. But two of these electrons are right in here. Right? So the total number of electrons in their valence shells would be 4, 5, 6. Would be 6 electrons here and 1 electron there. 7. Yeah, 6 and 1 is 7. That's just valence electrons. So notice, if we're just looking at the p orbitals and the s orbitals, well, that's not true. It's like this. It's like this when they're not bonded. Now, if we add them together, that's 6 and 1 is 7. But this one goes over here. Well, actually, there are 2 of them. Right? We can't complete oxygen with just 1 hydrogen. We need the other one. So from this one, we get an electron here and the next one here. So that makes it P6. And we get 1 electron here, makes that one 2, and makes this one 2. So this isoelectronic series, I use that term, didn't define it. Isoelectronic series, oh, we did that. We have done isoelectronics, haven't we? When we were doing electronic configurations. Yeah, I think we were discussing that. So we're bringing that up again. These isoelectronic series have the same electronic structure. So that means if you fix one as neutral, and in this case, we're letting the noble gas be neutral, everybody else has to be charged. Right? So you add 1 electron to fluorine and you get the same electronic structure as neon. You add 2 to oxygen and you get neon. Take 1 away from sodium and you get neon, 2 from magnesium, 3 from aluminum, and they all look like neon. So that explains why the preponderance, the preference for these elements, particularly in ionic compounds, is to form a 2- charge for oxygen, 1- for fluorine. This is all the chalcogens. This is all the halogens. This is all the alkaline metals. This is all the alkaline earths. And this is all the aluminum group. Well, most of all of them. That's why you get those charges. In the beginning, we just had, I told you to memorize them, right? But this is why they happen. All right, we're not going to spend a lot of time on this one. One example of another electronic series, isoelectronic series, just start at argon. If you start at argon and you move backwards to chlorine, sulfur, phosphorus, you're adding electrons to get them to look like argon. So we added 1 to chlorine. If you go the other direction, then you have to go down from argon to potassium, which is in the next period. And it's 1 removed from argon, so you take 1 electron away. Calcium's 2 removed, take away 2 electrons. So here's the electronic configuration of each one of these species, because that is the electronic configuration of argon. And this will be the same configuration for each one of these. All right. They have different protons, obviously, because they're different elements. That rule hasn't changed. Okay, we've looked at these trends for atomic size. We didn't look at ion radius per se. There may have been a review question on that. Ionization energy, we looked at that. We know electronegativity now. I left out electron affinity. But electron affinity is sort of second cousin to electronegativity. Now we're going to look at electron configurations, prediction of formulas for ionic compounds, covalent bonding, polarity. In fact, we've covered those. Yeah. Periodic trends in the table allow us to say something about each one of these. One element relative to the other. So what are the factors that influence the stability in the structure of binary ionic compounds? We're interested in that question. We're also interested in the question, how strongly do the ions attract each other in the solid state? And that is indicated by lattice energy. So we're going to look at lattice energy. Define lattice energy, and then how do you calculate it? Okay, lattice energy is, let's see. I don't want to steal all the butter. Well, yeah, we've got a formula coming up. Let's define it in terms of electrostatics. All right. When you have separated gaseous ions, let's say you have sodium ions here as a gas and chloride ions here as a gas. You bring them together and they make sodium chloride solid. What are they going to do? Are they going to absorb energy or release it? My guess is they're going to give up a lot of energy. The energy, because they're separate now, when they come closer together, by our own assumptions from the beginning, is the stability is increased because the energy here is lower than the energy here. So we're giving up energy here to get to that point. This is the lattice energy. So lattice energies are going to have a negative sign because energy is leaving the system. Now we can calculate lattice energy. All we need to know is charges on the ions, the distance between them, and some proportionality constant. This may not be Coulomb's constant, like we did before. This could be something different. And it may be specific for each combination of ions. Okay, here are the processes that take place when you get, now this is, what we're going to talk about now is not lattice energy. What we're talking about now is energy of formation. So I think we discussed that before. When you form a compound, let's say, well, I'll say sodium chloride. Remember, you start off with 1 mole of the product. We did talk about this, I'm pretty sure. Energy of formation. And then you work back from the most stable form of the element at 1 atmosphere and room temperature. So that's sodium solid, and that's chlorine, dichlorine gas. Okay, this would be the energy of formation. I think we put it this way, the enthalpy of formation. Okay, now buried in there is this lattice energy. How do we know that? Because there's the product, there's the product. So the last step should be the lattice energy, but it goes through several steps. And this is kind of like our discussion of solutions, right? The three-step process of making a solution. Take the solute and you have to tear the atoms apart, the molecules apart. Then you have to make room for them in your solution, the solvent, right? And then you put them together and the solute goes into those holes we just made. A three-step process. This is more than 3 steps though. So if we're starting from here, we're going to take this solid, and the first thing you do is when you add energy to it, you take this and turn it into a gas. Right? So our example here is a generic metal. You make a gas out of it. That's endothermic. You got to put energy into it. Break the bonds. The bonds that are holding that solid together, turn it into a gas. Then you're going to take that gas and ionize it, right? Because this is an ion and that's an ion. So we got to get it into an ionic form, and metals are going to be positive. So we put energy in. This is the ionization energy right here, right? Recognize that equation? Okay, now we've got this form right there. The metal, charged metal gaseous state. Now we're going to take the non-metal, right? If it happens to be this, and maybe it's already a gas. So in this case, we're assuming diatomic. So we take actually a half of this to balance the equation, a half of that one to make one of these. Okay, we're in the gaseous state, but we're not charged yet. And that's still endothermic. We got to put energy in to get there. Then we take this one, the single atom, and we attach an electron to it. That's exothermic. This is electron affinity. Recognize that equation? Electron affinity. So this is exothermic. Now we've got this ion and that ion, bring them back together. And that process going from here to the solid is extremely exothermic. Very, very high energy release. But if we add all of those terms up, as long as they're balanced, we add them all up, we get the energy of formation here. But the last step is the lattice energy. And this is an artist representation. We did several steps. A lot of these steps are endothermic, and then a couple of them are exothermic. Oops. There we go. So this just takes an example, right? We write out the formation equation for lithium fluoride, and then we go through each step, and we determine that the energy for this step is that's not a sign there. That's not a sign, because it needs to be positive if we're a sign. I think that's misleading, because we're adding energy to get there. So it should be a positive value for each of these steps until you get to the dissociation of the fluorine molecule. In this case, we have to add energy, and it's in that amount. Right? Now we've got the signs correct. This is an exothermic process when electron affinity is a negative value. And then the energy involved here is significantly greater. This is the lattice energy right here. If we add all those together, we should get a value of overall change, minus 617 kilojoules per mole for the formation of lithium fluoride, which is pretty high value. And the value is going to be much, much higher if electronegativities are very far apart. And lithium and fluorine are on opposite ends of the periodic table, so this value is going to be one of the higher ones. If you move closer together, like if we had magnesium sulfide, then the value should be much lower. Okay, so there we've added everything together that we determined each of these steps, 1, 2, 3, 4, 5 steps to give us the overall heat of formation for lithium fluoride. And the last step is the lattice energy. All right, so I mentioned earlier on, we can say qualitatively that a bond is ionic, nonpolar covalent, or polar covalent. But we can also express what percent of that covalent bond is ionic. How much of it is ionic character? And this is simply a way to do it. Let's see. You measure the dipole moment of this bond, and you calculate the dipole moment of, that's Coulomb's law, the dipole moment of X plus and Y minus, and compare them. Right? If the measured amount is equal to the calculated amount, then it's purely ionic, which rarely happens. And if you do that and put it on a chart, and the x-axis is the difference in electronegativity between the two atoms, right? So the greater it is, the more ionic you would expect, and the greater it is, the higher you find them in this scale of ionic character. Right? Lithium fluoride is the highest ionic character of all. But notice it's not 100%. Right, so the measured amount, the measured dipole for lithium fluoride is less than we would expect for lithium plus and fluorine minus ions. All right, so we have an operational definition. I remember when I was in graduate school, one of the professors that I discussed my program with, in fact, he was on my committee. I was concerned with how to express a certain type of extraction process I was using on soils to get certain elements out. And he said the best way to describe that is it's operationally defined. In other words, it's whatever you say it is. So here we are, an operational definition of the ionic compound. Any compound that conducts an electric current when melted will be classified as ionic. Now, I think I've mentioned this before. If an ionic compound is in crystalline form, those ions are locked in place. So if you put a positive pole on this side and a negative pole on that side with a light in the circuit and a battery, the light will not light because those ions have to be mobile to carry the current. But if you melt it, then they're free to move. But if you melt a substance and it doesn't conduct electricity, then it's not ionic. Like if you have a cube of sugar and you melt it and then put your electrodes in there, you won't conduct electricity. It's not ionic. That's an operational definition. Okay. So now we're going to talk about theory. And the reason I know we're going to talk about theory is because of that word right there. All theories have, well, not all. If you're talking about a model, then you're definitely talking about a theory. If you have a theory, you may or may not have a model. Most of the time you do have a model. And a model could be something as simple as a three-dimensional physical representation of what's going on at the microscopic level. Or it could be a mathematical expression that explains what's happening at the microscopic level. But it's always an attempt using the theory to get at what's actually happening where you can't see it. So what are the properties of a model? Well, first of all, we have to realize that a model is not reality. Okay? A model is a representation of those factors we think important so that we can manipulate them and try to learn something about what's happening where we can't see it. And when we make those changes to the model, then we ask the question, does the change that I made to my model, is it reflected in response to the real system? If it's not, then you made a change that's not valid in your model, or your model is not valid in that respect. So the model is not reality. Models are, like I just said, they only contain those factors that we consider important. So they're oversimplifications. And they have to be. Right? If the model gets too complex, then you can't use it. At least I wouldn't be able to. Maybe use a model that I can't because they understand the factors better than I do. So since they're oversimplifications, very often they're wrong. You have to go back to the drawing board. Models tend to become more complicated over time. We call that tweaking. Tweak your model to make the model fit reality. And if it doesn't get too far off track, you might start off with a simple model that's a regular geometric structure, say, and you tweak it this way, and now it's got a branch, and it's got another branch over here, and these branches tie together. And pretty soon it looks ugly. One thing that's sometimes overlooked is you must understand the assumptions that were made when the model was constructed. Because in order to simplify the model like this, you've got to make some assumptions. And that, in my way of thinking, is one of the major pitfalls for the climate models that are being used, because none of them work. And I think the ones who are proposing these models are so invested in proving that the earth is on fire and we're all going to die soon, that they overlook even the assumptions that they made in the first place when they constructed the models. But just because the model is wrong, you discover it's wrong at some point, doesn't mean it doesn't have its uses. I mean, it teaches you something about the system that you're investigating because your model doesn't work anymore. And if you ask intelligent questions about why didn't my model work, you might be able to learn something about the system that way as well as you would if the model was actually working. All right, what do you do when a model stops working? Or when a theory goes wrong? I may have said this already, I bet at the very beginning. It bears repeating. We have two choices. You can restrict the application of the model. Just say, all right, under these circumstances, it works okay. Under those circumstances, don't use it. Right? And I think my example was classical physics, the laws of Newton. Under certain circumstances, Newton's laws will not work. If things get really, really, really big, like neutron stars or black holes, Newtonian physics does not work, so we don't use it there. we use relativity. Or if things get really, really, really small, then we can't use it there either. That's when quantum mechanics comes in. What are your other options? Well, you can tweak the model, for a while until you keep it working, as long as the tweaks make sense. Right? It can get really ridiculous because some physicists now propose 26 dimensions, right? Not just height, width, depth, and time as the 4 dimensions of space. I can remember 30 years ago, they were proposing 11 and 12 dimensions. Now they're up to 26, right? And these are all mathematical constructions, right? I can't imagine 26 dimensions in real space. It just doesn't, it does not compute. Or, as a last resort, throw the model out and start over again. Those are your 3 choices. Oh yeah, like J.J. Thomson's plum pudding model of the atom, right? It defied the evidence, and there was no way you could tweak it and make it better. So throw it out. And then we went with Rutherford's nuclear model of the atom. That reminds me of medieval times when people were trying to explain the movement of stars and planets in the heavens. Right? If you assume that the Earth, the church was telling us that the Earth was the center of the universe. So they went through unbelievable gyrations and geometric progressions and gyrations to make the planets move the way they wanted them to. When all they had to do was listen to Copernicus and put the sun at the center. And then everything just, no more problem. Well, we needed Kepler to give us our 3 laws of planetary motion. But the model was better as a sun-centric model than an Earth-centric model. Okay. What can we say about bond energies? Right? Every bond has a certain energy associated with it, and it's based upon the fact that if we have a bond between these 2 atoms, then if we put enough energy into it, the bond will break. So that's considered the bond energy. How much energy does it take to break that bond? That would be an endothermic process. You have to add energy. Right? If these 2 separate atoms come together, then they should give off the same amount of energy that we had to put in to break the bond. So it's a 2-way street, you just change the signs. Single bonds, now we're talking about covalent bonds. Single bonds share 1 pair of electrons, and we always write that as a single dash. Double bonds have 2 dashes, 4 electrons. Triple bonds have 3 dashes, 6 electrons. Now, the trend is, as you go from single to double to triple, the bond shortens and the bond energy increases. But it's not a linear increase. In other words, a double bond is not twice as strong as a single. It's stronger, but not twice as strong. And same thing for a triple. Here's a list of bond energies, and this came straight out of your textbook. So if you have a molecule with this bond, then we know it takes 432, and I think that's kilojoules per mole of these bonds. I don't know why it doesn't let that units of measure off here. So you see differences in bonds here. Now, why do I have this list of bond energies up here? Because you can use this information to determine the enthalpy of a chemical reaction. Let's see. Ooh. Oh, I've gone beyond the class time, haven't I? Yeah. I'm going to bleed over into lab time, just so we can get this all done. Let me check the schedule and be sure. Oh, we do have a buffer. Thursday's a buffer day, right? So let me find a convenient place to break.
It has a place to stop. It's like three more slides and then we stop.
Oh, I have a slide for stopping?
Yes, it says pause until next.
Oh, okay. All right. So in three more slides, we'll stop because the slide set tells me to. Okay, so if we know the bond energies of each one of these bonds, then we have a molecule that's got these bonds in it. We know what the energy content of that molecule is, or what it would take to break it all apart. But if we bring those together, we can form bonds and we get that energy back. So what that means is, if you can take all the bond energies that are associated with the reactants and subtract the bond energies of the products and subtract the bond energies of the reactants from it, you can find out what the enthalpy of that reaction is. And we'll do that. And it's been compared to actual measurement of reaction energies, the enthalpies of actual reactions compared to this method, and they're, what's the word, simpatico. They're right equal to each other. Okay, we've already said this. I'm not going to stop here. So here's that equation. I just give it to you in words. Here it is on the board. So in order to determine the enthalpy of a reaction, what we can do is take the bonds that are broken. Well, actually, I had it backwards. The energy that's required to break the bonds, right? That's a positive value. Subtract the energy that's released when the new bonds form. Right? So it's not products minus reactants, it's reactants minus products. And that's a consequence of the signs, right? Because this is energy input. This is positive, and these are going to be negative. But we subtract them, so that makes them positive too. This term right here is the Greek letter sigma. Right? If you've had, I don't know, some courses, non-math courses use it, but it's the Greek letter sigma is their capital S. And it's used in mathematical terms to mean summation. So you take the summation of the bond energies. And you always have to use this value here. What is N? In this formula, you take the balanced chemical equation, and N is the coefficient. That tells you how many of those bonds were broken. So if you have say you have H2O, or yeah, say you have like this, like that, but you have three of them in this form, in this balanced equation. Then if you have the OH bond energy, then you know you're going to need 3 of these and 3 of these. That means you need 6 of those. That's what the N means. So here's an example. Notice where we have CH3N triple bond carbon and CH3C triple bond nitrogen. The only thing that's changed is the position of the carbon and the nitrogen. Right? So that would look like this. We would have here, 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 and here. That's the CH3. Then on this side, it would be bound like that. And on the other side, it would be like that. Okay. So all you've done is you've broken this bond and flipped it around. to make this bond. So really, the only bond that we need to be concerned with, because if we break these bonds and reform them, right, it's a wash. So really the only one we want is break that bond, CN, single bond here, and form CC. Right, so this one minus that one. And the difference is minus 42. Because there's only one of them. Right, so this one, 305 minus 347 is minus 42, which means our enthalpy should be exothermic. This should give up energy, this process. Okay, we're gonna pause. Come back on Thursday. And we only have one lab left. The Dumas method for determining a molar mass of a volatile compound. And that'll be next Tuesday. You can find it on Brightspace, or if you come to class, I'll give you a hard copy on Thursday.